Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, Lesson 1, Integer Exponents. So now we're in Module 3. We're going to start talking about exponents here. We're finished with trigonometry and the identities and all that for now. And I have a new picture behind me. So that town back there is called Malvania, Sicily. And that is an extinct crater on Mount Etna called Monte Mojo. Okay, so integer exponents. Opening exercise. Can you fold a piece of notebook paper in half 10 times? So here is, my camera's not working properly. It's not picking it up like a green screen. Anyway, I've got this piece of paper. That's not going to work well because it's yellow, I bet. It's like a green screen. So let me get a piece of computer paper and we're going to see how many times we can fold it. See if this shows up better. No, white doesn't work either. It's invisible, making me invisible. Okay, so anyway, we got this piece of paper. Does it work back here? Nope. Okay, anyhow. What you're going to do is fold, where is it? This piece of paper right here. And we're going to fold it in half 10 times. So there's one. Can't see it. If I shake it. Hello. Okay, I folded it once anyway. Gonna fold it a second time. There's two. Catch a glimpse of it here and there. There's two. Question is, can we fold it 10 times? There's three. Getting smaller, there's three. 4. Okay. I'm going to have to say probably no. Okay. There's 5. Piccolo, small. There's 6. Coming up. 6. 6. 7, and I'm not even going to attempt 8. So there we have it. 7. So can you fold a piece of notebook paper in half 10 times? Nope. How thick will the folded paper be? Well, I just folded that in, I don't know, a few centimeters, I guess. 3 cm maybe. Will the area of the paper on top of the folded stack be larger or smaller than a postage stamp? Okay. Well, there's different size postage stamps, so that's not a very good question. There's big postage stamps, there's small postage stamps. Anyway, I would say that is smaller than a postage stamp. Okay, so anyway, you're supposed to do that in class as an activity. And what's happening to the area as you fold it? Obviously, the area is decreasing and the thickness is increasing with the number of times you fold the paper. Okay, so then there's an exploratory challenge. What are the dimensions of your paper? Okay. All right, I used a standard sheet of paper. So what are the dimensions of your paper? Are they asking if it's folded or no, it's before folding, I guess. So I would say it is 8.5 by 11 inches. Standard sheet of paper. How thick is one sheet of paper? Explain how you decided on your answer. Okay, 0.05 to 0.1 millimeters. Explain how you decided on your answer. Okay, describe how you folded the paper. All right, so there's different ways you can fold the paper. You could have done, you know, back in elementary school, I think they called it hamburger and hot dog fold. So that's what they're saying there. Describe how you folded the paper. I did hamburger, 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 fold. And then I just kept folding it different ways. So you just have to explain how you folded your paper there. I'm just going to leave mine at that. Answers will vary. Okay, so before I go on, I'm going to stop here and go back to part B. And if we don't have access to the internet like I do, and while making this video, I just Googled it. What you could do is say, well, a ream of paper is 500 sheets. It's about 2 inches high. Divide 2 by 500, and that'd give you a thickness of 0.004 inches. I was measuring in centimeters. That would be inches. Okay, you could do the same in centimeters as well. If we knew how thick 500 sheets were, divide that by 500. Okay, so what would a description of a fold be? So I will bring in an example of a description of a fold rather than just saying hamburger fold. Okay, so here we go. First, we folded the paper in half, so that was 8.5 inches by 5.5. So that explained that you folded it the hamburger way. 11 divided by 2 is 5.5. Then we rotated the paper and folded again, so it was a 5.5 by 4.25 inches. Then we rotated the paper and folded again, and so on. So there's a better description of how we folded the paper. All right, page 2 brings us to part D, and it says to record data in the following table based on the size and thickness of your paper. All right, so rather than actually doing this and measuring it, I'm going to bring in solutions and we'll discuss it. Okay, so here's what D could look like. So if we didn't fold it and we took that 2 inches divided by 500, no folds, the thickness of the paper was 0.004 inches. Fold it once, the thickness is going to double to 0.008. Fold it again, that's going to double again to 0.016. 0.032, 0.064, 0.128, 0.256, 512, 1024, 2048, 4096. Okay, anybody who's played the 2048 game, that's basically what this is. See how it's doubling, and there's 2048. The other thing is gigs on a hard drive. So you can get a phone that's 64 gig, 128, 256, 512, 1024, 2048, and so on. And so that's another place that shows that numbers are doubling. So it says area of the top of the stack, well, 8.5. So where did they get these? So let's just take a look with a calculator. A sheet of paper is 8.5 by 11. So the area is 93.5 square inches. Fold the paper in half and it became 8.5 times half of 11, 5.5, enter. And that's where that 46.75 came in. Fold it in half again, the 8.5 would become 4.25 times 5.5, enter, and you get 23.375, and so on and so on. And that's where these values came in. So it says answers are rounded to 3 decimal places after the 5th fold. So once we got to the 5th fold, they were going out 6 decimal places. Then they started rounding to 3 decimal places after that. Okay, so the answer says, or the question part E says, were you able to fold a piece of notebook paper in half 10 times? And I was not able to. The answer is no. I only got 7 on mine. You might have been able to get 8, but I only got 7. So let's bring in that answer. Okay, so the answer is no. It got too small and too thick for us to continue folding it. Part F says to create a formula that approximates the height of the stack after n folds. Okay, so if we're going to create a formula, h is height, n is folds. What we're calculating is thickness. So a formula would be height with respect to the number of folds, h of n equals the thickness of the paper times, and since we are doubling this, our base is 2. Okay, 2 times 0 is 1, 2 times 1 is 2, 2 squared is 4. I should say 2 squared is 4. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. So it's doubling every time. So it's going to be to the power of n number of folds. So if n is 0, 2 to the 0 is 1. Thickness that we started with, which was 0.004. So this would be h of 0 folds would be 0.004 times 2 to the 0, which is 1. So it would be 0.004 times 1, which is 0.004. Change n to 1, and that'd be 0.004 times 2 to the 1, or simply 2, and 0.004 times 2 is 0.008. I just check a few of these, make sure it sounds right. And then for n equaling 2, I'd put 2 to the n, which would be 2 squared, which is 4, and 0.004 times 4 is 0.016. So it looks like it's working. Let's do one more, or we could skip and go to, say, 10. So 0.004 times 2 to the 10th, and then I could check with my calculator. 0.004 times, not plus, times, not plus, times. 0.004 times 2 to the power of 10. And we got 4.096. And there it is right here. Okay, so there's the answer. H of n equals t, where t is thickness, times 2 to the n, where n is number of folds. G says create a formula that will give you the approximate area of the top after n folds. So we're going to start off with the area formula. So area of, based on the number of folds, is going to equal, and this takes a little bit more thought. Okay, so what you have to think about is what's happening to the paper. So the area, what is the area doing every time you fold it? Well, if I had a piece of paper that was, let's say 10 by 10, just to make it easier, and I folded it in half, now it's 10 by 5. It would look like this, folded in half. This would be 5, and this would be 10. Well, the area of the 10 by 10 was 100, and the area of this is 50. Then if I fold it in half this way, I would now have a square that's 5 by 5, because this 10 would have been cut in half this way. And that would be 25. So what's happening to the area? 100, 50, 25. The area is getting cut in half. So that's going to be our base, a base of 1/2. The first fold would be a sub 0, a naught. So times 1/2 to the power of the number of folds is what it would appear to be. So if I take the area of a piece of paper, let me get this out of the way now. Okay. So 93.5. So this would be 93.5, the area of a piece of paper with 0 folds, that'd be 0. This would then be 0. 1/2 to the 0 is 1. 93.5 times 1 is 93.5. Okay. So now if I check 2, a sub 1, or the area after one fold would be 1/2. So a sub 1, you would say a sub 1 equals, a of 1 equals a sub 1 times 1/2 to the 1. Okay, actually, no, that stays 0, a sub 0. So what we're taking is the area without folding it, the starting area, 93.5. 1/2 to the first power is 1/2. Half of 93.5 is 46.75. Okay, and then it looks like it is working. So now I'm going to change this to a sub something else. And how about I pick 7 just to check? So let's check a sub 7, which would be a naught 93.5 times 1/2 to the 7th power. Okay, so if I use my calculator to figure this, then it'd be 93.5 parentheses 1/2, which is 0.5, to the power of 7. And when I hit enter, I get 0.73046, and there's 0.730 rounded to 3 decimal places. So the formula is definitely a sub n equals a sub naught times 1/2 to the power of n, where a naught is the size of the paper without any folds, and n is the number of folds. Okay, so part H now says answer the original question from the opening exercise. How do the actual answers compare to your original prediction? So what was the opening exercise? First question, can you fold a piece of notebook paper in half 10 times? So in order to fold it in half 10 times, what would be the area for starters? Can't write with an eraser. Area of a 10 fold would equal a naught, which is, scroll too far, 93.5 times 1/2 to the 10th power. And that would equal 93.5 parentheses 0.5 to the 10. And that is 0.0913. So 0.091, it would be the area. Less than a hundredth, or less than a tenth of an inch. Think about that. A tenth of an inch. Take 1 inch. Okay. A distance this long, divide it into 10. So this, it would be 1/8 is right here. That would be an eighth. A tenth is a little bit smaller. Do you think you could fold a piece of paper so that the area would be that small? And I'm saying no way, no how. All right. So then we also could have said, well, let's see, h, the height. Actually, the thickness doesn't, well, we could still do it. H of 10 equals thickness, which was 0.004, I believe. Yes. Times 2 to the 10th. So if I put that in my calculator, 0.004 parentheses 2 to the 10th, the thickness would be 4.096. The height, inches, 4 inches thick. Okay, so that would be from here to here. That's pretty thick. Okay. Don't think we could get the paper to stack up that thick and be as small as we said, which was a tenth, which is less than an eighth, which would be a piece of paper about that big around, this tall. Okay, so there is our investigation into folding paper. Okay, page 3 brings us to example 1, using the properties of exponents to rewrite expressions. So the table below displays the thickness and area of a folded square sheet of gold foil. Okay, kind of like the foil used to wrap candy or chocolate. In 2001, Brittany Gallivan, a California high school junior, successfully folded a 100 square inch sheet of gold foil in half 12 times to earn extra credit in her mathematics class. Rewrite each of the table entries as a multiple of a power of 2. So we're going to use, for the thickness, we're going to use, that's going to be the height, with n being the number of folds, equals, or yeah, the height equals the thickness times the thickness of the foil, which is 0.028 millionths of a meter, times 2 to the number of folds. Okay, so 0 folds would give us 0.28 millionths of a meter times 0.2 to the 0, which is times 1, which will give us this 0.28. And then this 0.56 came from taking the original thickness times 2 to the power of 1 being 1 fold. And we just continue with that. It's 0.28 times 2 squared, 0.28 times 2 to the power of 3. Okay, 0.28 times 2 to the number of folds, 4, 0.28 times 2 to the number of folds, 5, and finally 0.28 times 2 to the 6. Okay, and then the area is decreasing. So if we take a sub n, a of, not sub, a of n equals a sub naught, which is the area without folding it. So it was a 10 by 10 square sheet of foil. 10 times 10 is 100. And we're going to multiply it by half because that's the base. When you fold something, it is then half the area to the power of n, which is the number of folds. We got that, we derived that last page. So if you take 100 times 2 to the no folds, 2 to the 0 is 1, 100 times 1 is 100. Okay, but here's where it gets a little tricky. I think you covered this in Algebra 1. If you have, let's just stop here a minute. If I said 2 to the first power, that just means 2. Okay, and then if I take that same 2 to the 0 power, well, that equals 1. Because anything to the 0 power is 1, and that comes from 2 to the 0 is, let's just say, let me think about this a second. Okay, let's just say I had 2 cubed and I divide it by 2 squared. Well, that equals 2 times 2 times 2 over 2 times 2. And these 2's cancel, these 2's cancel. And we're left with just simply 2. And that is 2 to the 1, which equals 2. And that just shows, that comes from our rule with exponents. When we're dividing, same basis, the exponents get subtracted. So this would actually be 3 minus 2. So it'd be 2 to the 3 minus 2 equals 2 to the 1. Okay, which is 2. So where the 0 comes from is if I had 2 cubed divided by 2 cubed, well, that's 2 times 2 times 2 over 2 times 2 times 2. They all cancel out, or you could think of it as anything divided by itself. That's 2 to the 3 minus 3, which is 2 to the 0. Anything divided by itself is 1. So that's where 2 to the 0 comes from. That's why 2 to the 0 is 1. So then when we start getting into negatives, let's get rid of all this. Okay, what happens when we have a negative? Well, that's going to happen when the denominator is larger. So if I had 2 squared divided by 2 cubed, that would be 2 to the 2 minus 3, or 2 to the negative 1. So if I wrote it this way, 2 times 2, and this is 2 times 2 times 2, these 2's cancel, these 2's cancel, and that would leave me a 1 on top and a 2 on the bottom. So 2 to the negative 1 is 1/2. Another way you could think about it is 2 is 2 over 1. Negative exponent, if we take the reciprocal of what we're taking the power of, that will change the sign to positive. And 1/2 to the power of 1 is 1/2. So there's a quick review of negative exponents. Hopefully that made sense to you. And let's now continue with these negative exponents. Okay. So 100 times 2 to the negative 1. 2 to the negative 1 is a half, right? Remember I showed you 2 to the 1 to the negative 1 would be the same as 1/2 to the positive 1. So 100 times 1/2 is 50. 100 times 2 to the negative 2. Okay, so now if I change this to a negative 2, okay, 2 over 1 to the negative 2 is the same as 1/2 squared, and 1/2 squared is 1 squared over 2 squared, which is 1 over 4. And 1/4 of 100 is 25, okay? So I just want to do a couple of those to solidify that. So 100 times 2 to the negative 3 would give us 12.5. 100 times 2 to the negative 4, and you get the idea now. 100 times 2 to the negative 5, and 100 times 2 to the negative 6. So as our exponent goes negative, larger in the negative direction, the number gets smaller. Okay, example 2 says, applying the properties of exponents to rewrite expressions. Rewrite each expression in the form k times x to the n, where k is a real number, n is an integer, and x is a non-zero real number. Okay. Okay, there are a couple of different ways we can do this. Here's one way. You can rewrite this as 5 times negative 3 times x to the 5th, which is 5x's, times x squared. Okay, so 5, negative 3, x to the 5th, x to the 5th, x squared, x squared. Well, positive times a negative is negative. 5 times 3 is 15. And now I have 5 x's and 2 more, so that's going to be x to the 7th. So remember, when we're multiplying, you multiply the coefficient, okay, coefficient, number in front of the variable. You multiply the coefficient and you add exponents. X to the 5th. So x to the 5th times x squared equals x to the 5th plus 2 equals x to the 7th. Okay? All righty. So that's what we're doing here. So here I'm going to simplify this. Please pay attention to the parentheses. We have to do that first. So 3x to the 5th is not in parentheses. I can just rewrite that. This 4 must get distributed to both portions. 2 to the 4th power is 2 times 2 times 2 times 2, which is 16. And x to the 4th power. So the first thing I had to do is distribute throughout that parentheses. So you could think of that as 2x times 2x times 2x times 2x times 2x, 4 times. Okay? So this is going to simplify. 3 over 16, I cannot reduce. 16 will not go into 3. Okay, and the way I do it in class is I say you have to subtract. So it's x to the 5th. You could rewrite it as this if you wish. Once you get the feel for it, you don't have to do it anymore. You say x to the 5 minus 4. That's just showing the rule. When you're dividing exponents with the same base, you subtract the powers. So this is going to yield 3 over 16 x to the 5 minus 4, which is 1, or just simply 3/16 x. Okay. And again, now we have another one that has parentheses. We need to address the parentheses first. So let 3 just hang out and wait for us. And remember what I said about a negative exponent. I will first take care of the negative exponent by saying 1 over x squared. And this exponent will now become positive. Okay. And now I'm going to distribute this 3 here and here. So that's going to leave me with my 3 still waiting. 3 times 1 is 3. And x to the 2nd to the 3rd, think of it as x squared 3 times. 2, 4, 6, that's x to the 6th. Okay? So now we're dividing a fraction by a fraction. So the rule says take the numerator and multiply by the reciprocal of the denominator. Okay? The 3's will cancel, and I get 6x. Or x to the power of 6 divided by 1, which is just simply x to the 6th. Okay, and I made a mistake there, so let me fix it real quickly. My apologies. 1 times 3 is not 3. Okay, 1 times 3 is not 3. So let me get rid of this and fix that. 1 to the third, or 1 times 3, or 1 to the third power is still 1. My apologies. And then that would be 3 over 1 times x to the 6th over 1, and that would give me 3x to the 6th power. Okay. Okay, page 4, one more example, D. Okay, so we have x to the negative 3 times x to the 4th over x to the 8th. So there's a couple of different ways we can do these, but let's just simplify the numerator first. So I'll just leave x to the 8th alone for now. And remember, when multiplying, okay, this is multiplication, x to the negative 3 times x to the 4th, we add our exponents, so that'd be the same as x to the negative 3 plus 4. And that's going to give us just x to the 1, or x over x to the 8th. Okay, remember that this is x to the 1. So this would become x to the 1 minus 8, right? Subtract, when you divide, you subtract exponents, numerator minus the power of the denominator. And this is going to give us x to the negative 7. But if I go back and look at my directions, it says rewrite each expression in the form of kx to the n, where k is a real number, n is an integer, and x is a non-zero real number. Okay, so it didn't say that n, being the exponent, is a positive integer. So I guess we're done right there with x to the power of negative 7. Okay. If I didn't want to leave it with a negative power, then that would also be equal to x to the 1, 1 over x to the 7th. Think of this as x over 1. So that'd equal 1 over x to the power of 7. Okay, but it didn't say that, so we can stop right here. All right, exercises 1 through 5. Now it's your turn. Pause the video, see if you can do these, come back and check your solutions. And speaking of checking, well, I'll get to that in a moment. So here we go. Rewrite each expression in the form k x to the n, where k is a real number and n is an integer. Assume that x does not equal 0. Okay, because like here, if x were 0, 0 to the 8th power is 0. 0 times 3 is 0. 1 divided by 0 is undefined. So x cannot be 0. All right. So we have a coefficient 2 times a coefficient 1. So I'll put those together. And then we have an x to the 5th and an x to the 10th. So that's the setup. 2 times 1, x to the 5 plus 10, and we're done. Okay. How do I know I did that correctly? Let's just say this was a quiz or a test that your teacher gave you, and you get this answer, and you're allowed to use calculators, which using a calculator here with the variables will not help you, but it will if you know how to use the calculator. So here's what you do. You do the problem, and then you're like, okay, well, 2x to the 5 times x to the 10th. How do I know that that is the correct answer? How could I check that? Well, I can store a value in my calculator for x. I don't like using 0, obviously, because everything, if it's 0, everything just turns out to be nothing or 1. If it's 1, it doesn't change anything when multiplying. If it's 2, I don't like to use 2 because 2 squared is equal to 2 plus 2. So I like to use numbers 3 or greater. So I'm going to take and store a value of 3 in my calculator for x. So I turn my calculator on. I press 3 for the number 3. STO is right here. I press that and I get this little arrow on my screen, and then I hit the variable button and I hit enter. So now it's telling the computer, or the calculator, which is a computer, that x equals 3. Okay, so now if I said 2x, well, what's 2 times 3? It should be 6. And sure enough, there it is. So it just remembers that x has to be 3 all the time. So I can use that to check my answer. So then I put my original problem in, 2x to the 5th power, okay? And I'm going to say times x to the power of 10. So there's the original problem, 2x to the 5th times x to the 10th. And I hit enter. And I got this really big number, 28,697,814. Okay, yeah, so what's that going to do for me? Well, you take your answer, and if this is equivalent to that, then you should get the same answer with x being 3. So then I say 2x to the power of 15, and I hit enter, and there is my verification that I did the problem correctly. Okay, that's the only time I'm going to show that. If you need to see it again, you can rewind the video. So here we go. Let's check the rest. So 1 over 3 times x to the 8. Rewrite each expression in the form of k x to the n. So we don't want fractions. So this is going to equal, think of this as 1/3 times 1 over x to the 8. Okay, the x is not in parentheses, or the 3, there's no parentheses here, so we can split this up like so. This is going to give us 1 over 3 times x to the negative 8 over 1, which is the same as x to the negative 8 over 3, or 1/3 x to the negative 8. All right, number 3. Again, that's interesting. 6 over 1. Okay, I'm going to isolate the coefficients. Times x to the negative 5 over x to the negative 3. I'm just showing all my work here. That is going to equal 6 over 1 times x to the negative 5 minus a negative 3, which is plus 3. And that's going to equal 6 over 1 x to the negative 2, which is simply 6x to the negative 2. Okay, number 4. Now notice there are parentheses here, so I'm going to address the parentheses first. I'm going to distribute 3 to the negative 3 is 3. First of all, I'm going to flip this. So it's going to be, so disregard that. I don't want to distribute a negative. I'm going to take the reciprocal, which would be x to the negative 22 over 3. In doing so, the exponent outside becomes positive. Okay. I'm now going to split this up, and that is going to be 1/3 cubed times 1 over x to the 22. Notice what I did there? I flipped that 1 over x to the negative 22 to make this positive, and that's also going to be to the 3rd power. So that's going to equal 1 cubed is 1, 3 cubed is 9, and times 1 cubed, which is 1, and x to the 22 to the 3rd power is 66. Okay, so this is going to equal 1 over 9x to the 66. Or we could say, take its reciprocal. I just said 9. 3 times 3, it's not 9. 3 times 3 times 3, 3 squared is 9. This should be 27. So this is 27. And this is 27. And how would I know I made that mistake? Put your answer in the calculator, put the original in the calculator, see if they match. Okay, so 1 over 27x to the 66 can be rewritten as 1 over 27 times x to the negative 66. Okay. Number 5. I'm going to get rid of the parentheses first. That's going to become x to the 2n, because power of power you multiply. And that's going to be times x cubed. And that is going to be x to the 2n plus 3, because that's the rule for when we multiply, we add the exponents. So the answer to that one is x to the 2n plus 3. Okay, and I'm going to do something here. I'm going to check this one too, because it has two variables. So we're going to leave x as 3, but we need to give n a value. And where is n on my calculator? Well, alpha is the green button, and you see these letters in green on here. N is right here. It's the log button. So I'm going to do parentheses, x squared. Okay, I'm just copying this problem right here. Close the parentheses. To the power of, oh wait, first I have to give n a value, my fault. Let's use, I don't know, 5. 5 store alpha n. Enter. So now n is 5. X is still 3. So if I hit X and hit enter, 3. Okay, so now I'm going to put parentheses, x squared, close parentheses, to the power of alpha log for n, times x cubed. Enter. And I got 1,594,323. Okay, it doesn't really matter what this number is. You just put the answer that you got in, x to the power of 2 alpha log for n plus 3, all in the numerator, or all in the exponent. And I got the same answer. My answer is correct. Okay. Okay, page 5 brings us to the end of lesson 1, module 3. Review the lesson summary and go to your problem set.